Hello everyone. Uh, Today in this video, okay, let me first introduce myself. I am Malik Arslan Nisar, TA for this course, Introduction to Mechanical Vibration. So, we have already taken the live sessions for all the weeks, but however, there was a doubt among the students regarding the direction of damping force, like when we are considering or solving a system of this a multiple degree of freedom system. So, how do we calculate basically the damping force, and how do we basically write the direction of the damping force? Okay, so for that, I will consider two masses and which are connected by a damper. So in that, I will show that how do we determine the basically the direction of the damping force. Okay. So it is similar to the example we did in last class. Okay, I will maybe visit back to the example again so that you get a clear understanding. But right now, I would simply draw two masses with the damper, and I'll show you how to determine the direction. So let us consider we have a mass, say M1, which is connected to a damper, which is connected to a mass M2 with a damper. Okay, so these are basically our two masses, and we assume that it is obviously moving with a velocity x2 dot in this direction, and it is moving with a velocity x1 dot in this direction. Now one thing is that we know that direction of damping force is opposite to the relative velocity. Now this term here is important. Okay, so obviously it is talking about the relative velocity between the 2 points, that is the point on the mass and obviously on the damper if we are considering here. Okay, sorry, not on the damper, but obviously on the point on this mass m2 and the point on this mass m1. Okay, so let me consider those 2 points. I can call it point 2 and I can call it point 1. Okay, now let's focus on this mass m2 first. Okay, so if I draw the free body diagram of this mass m2, right? So tell me what will be the relative velocity of this point 2 with respect to 1. We know that it will be x to 1 dot, right? That is how we write the relative velocity of point 2 with respect to point 1. So it will be basically equal to x2 dot minus x1 dot. That is the definition of the relative velocity, right? Now the x2 dot minus x1 dot, and obviously I have assumed that x2 dot is greater than x1 dot here. Okay, so x2 dot is greater than x1 dot. This is the relative velocity of this point, and the direction is to the positive x. Okay, let me consider this is positive x and this is negative x. So it's to the positive x. Now we know that damping force will be opposite to this, so it will be minus times c of x2 dot minus x1 dot. This minus is determining nothing but basically the direction. So it tells me that on this mass, okay, which has a velocity of x1 dot to the positive x, there will be a damping force of magnitude c x2 dot minus x1 dot in the negative direction. Again, this negative sign here determines the direction, okay, to the left. So this is for mass m2, right? Now when we consider for mass m1, okay, so for m1 we have the damper on the right of m1. So here this is m1, this is the point 1 which I marked, okay, and this is the direction of the velocity. Now see, when I write the relative velocity of mass or point 1 with respect to point 2, or basically mass 1 with respect to mass 2, it will be relative velocity of 1 with respect to 2, okay, and it will be equal to x1 dot minus x2 dot, okay, right? This will be my relative velocity. Again, x1 x2 dot is greater than x1 dot, so this term will be negative, so it tells the direction of basically the relative velocity. Now obviously we know that damping force, again when we write the damping force here, okay, let me call it ft. So damping force in this case, okay, will be equal to minus of c into x1 dot minus x2 dot, okay. So this will be my damping force here. Now if you look clearly, it is, in the first case damping force was minus c x2 dot minus x1 dot, and here it is minus c x1 dot minus x2 dot. So I can write it as c x2 dot minus x1 dot. Now here this minus sign determines the direction to the negative x, right? Now here the direction, the magnitude is again coming out to be the same, but the direction is coming out to be positive x. So basically on this mass, the damping force will be in this direction, okay. The magnitude will be same, but the direction will be changed like this, okay, because obviously we consider the relative velocity while considering the points, okay. So this is the explanation of how we calculate the direction of the damping force. Now if I revisit the yesterday's class, okay, let me check, it's there, yeah. So this is the problem we solved in last class. Now in mass 1, I don't think there is any confusion, because obviously there is only one damper. The velocity is to the velocity of mass 2m here is to the right direction, so obviously the damping force will be to the left direction, because this point is fixed, so relative velocity direction is this way. Now the doubt was in this mass, okay. So for here, if again you see that the relative, I think the spring forces are clear how we got them. Now the confusion was in this. So here also, if you see, the this point has a velocity x3 dot, okay, and this point has a velocity x2 dot. So let me write it down here. So basically this point is x2 dot, and then there is a damper, and on the other side we have the point x3 dot. Now the definition says that the damping force is in the direction of opposite to the direction of the relative velocity. So here if I write the relative velocity again of the point 2 with respect to point 3, it will be equal to velocity of point 2 minus velocity of point 3, right? So this will be the relative velocity. So now since this is our relative velocity, the damping force will be opposite to it. So it will be minus c into x2 dot minus x3 dot, right? So this will be our damping force, and I can now take this minus sign to the inside, and it will be x3 dot minus x2 dot. Now obviously here it is positive, so this damping force will be to this direction. Okay, so that is why I have shown the damping force on this mass in this direction. Okay, on mass m2 in this direction. Now similarly, when we consider uh, wait a minute, yeah, now when I consider this mass, okay, so here again I am considering this point. Okay, so this now the relative velocity here will be relative velocity of x3 with respect to x2. Okay, so it will be x3 dot minus x2 dot, and the damping force will be in the opposite direction to relative velocity, so it will be minus c x3 dot minus x2 dot. So you can clearly see that it has a minus sign, so it will be basically to the minus x-axis. Okay, so that is why the direction is this way, and for this mass the direction is this way. Okay, so basically this is how you follow it for every mass, and there can be n number of this masses. Okay, the procedure will be similar, because obviously on the fixed masses you know that it's very easy to determine the damping force. Okay, because the damper one end is already fixed, so there is the relative velocity is basically the absolute velocity in that case, because the velocity of this point becomes zero. So on the ends there is no problem, but for the masses in between you will follow the same procedure even if the masses are increased to a greater number. Okay, for any n number of masses the same procedure will be followed. So basically that is how you solve such problems, and then thank you so much for watching this video, and all the best for your examinations. Okay, I will upload the week 7 video in a day or two, and so do prepare well, and once again all the best for your examinations, and thank you. So I will end this video here now. Goodbye.